All right, good morning, everyone. So I thought I would start off by sharing a beautiful example of when static friction turns into kinetic friction with my son yesterday. It was kind of a fantastic moment. So anyways, we were at the rink. We were trying to get our stuff off so we could go back home. And my son, instead of taking the 2 seconds to untie his skates because he's a kid, he doesn't want to do that, he just grabs his skate boot and keeps trying to pull off the skates. Needless to say, eventually he broke away the static friction, which turned into kinetic friction, which caused him to whip his skate up like this and hit himself in the forehead with his skate blade. It's kind of fantastic. Anyways, so my first reaction is he just cut his eye wide open because those things can be kind of sharp, but he didn't actually do that. There was no mark, so I kind of laughed at him after that. But anyways, perfect parenting. So I just thought it was a fantastic example of static friction gives way to kinetic friction. Anyways, so today we're going to start chapter 27. So 27 is going to be our first foray into now getting away from electrostatics into now electrodynamics. So we're going to start looking at now electrodynamics. So remember, electrostatics is when things were stationary, things were moving. So we had static electric charges, which is creating things like electric fields. But now we're looking at electrostatics where things are going to start to move, right? So what we're going to be doing is applying electric fields, applying potential differences, so that now charges will no longer be stationary. Charges are no longer stationary. But are in fact moving. So basically, we start looking at circuits. So this will bring us basically to start looking at circuits, which will bring us to looking at other interesting phenomena as well. So one thing to point out is before we said if we had a conductor, right, we said that there were no electric fields within a conductor. Now, this is technically only true in electrostatics. Which means that now we're going to be looking at electrodynamics, which means that there are going to be electric fields present, and we're going to know that's because the charges are moving. The only way to get charges to move is to apply a force to them, which means that we have to have an electric field which is present to cause these things to start to move. So this isn't necessarily true anymore in electrostatics or electrodynamics. Not necessarily true. In electrodynamics. So let's make note of that. So again, before we made a big deal of the fact that there had to be no electric fields inside, which means when we use Gauss's law, when we talked about a conductor, we knew the electric field had to be zero on the inside. But now in electrodynamics, things are going to be moving, but the only way to move them is to cause forces on them, which means there does have to be an electric field present. So before we move on, start talking about defining things, kind of first build you a picture. So I showed you this guys before, but we're going to show it again. This is what we're going to start looking at. So we're going to have batteries. These batteries are going to supply a potential difference again, which is then going to create a force onto the charge movers, which again, we're going to pretend are positive charges, but in reality, again, they're negative charges, which are then going to move through some sort of circuit and then hit something like this, which is then a resistor. Okay? Now, what's the point of a resistor? So basically what happens is, as this thing is causing an electric field, we know these guys want to accelerate. Because we know they have an electric force on them based on the fact that they have a charge. So we know the force is the same thing as the charge times the electric field. So these guys are going to start to accelerate through the wire, but then they're going to start running into these resistors. Now inside the resistor, I have atoms, which means that I'm going to try to accelerate these charged particles through these atoms, but as we talked about in lab, that doesn't really happen. And the reason for that is that the atoms are much, much heavier than the electrons themselves, which means that electrons are going to hit, undergo an elastic collision, which means they're going to bounce off, accelerate, hit again, accelerate, hit again, accelerate, hit again. Now, every time that they slam that into one of these atoms, when it slams, it's going to impart part of its kinetic energy then onto the atom, which is going to cause the atom to start to vibrate. Right? Which means that inside of the resistor here, the atoms inside the resistor are going to start to vibrate, which means they're going to also gain now their kinetic energy. So these electrons that are going to lose kinetic energy due to the collision, the atoms that are then going to gain kinetic energy to the collision, they're going to start to oscillate. And we know from kinetic theory from 205 that the greater that they oscillate, i.e. the greater the kinetic energy, the higher the temperature. Remember in 205 we said that temperature and kinetic energy were basically the same thing. So temperature is simply a measure of the kinetic energy, which means that the faster and faster these things are going to start to oscillate, which means if I, for example, crank up the voltage, these things are now going to start to oscillate more and more and more rapidly due to all these collisions, which means this thing is going to get hot. As this thing gets hot, that energy then now is going to be dissipated out to the rest of the world via heat. Okay? So what I'm going to do is I'm going to lose thermal radiation to the outside world because of these head-on collisions that the electrons are making then with the atoms on the inside. So these things are going to get hot. So the point then of a resistor is basically to lose energy from the system where that energy is lost due to the head-on collisions, the elastic collisions that the electrons are making with the atoms. And eventually that energy is going to be taken off as heat, lost as temperature. So I'm going to lose thermal energy. So this is the picture we're going to be working with as we go through this chapter. So we're going to basically go through and identify all of these different things. We're going to talk about currents, we're going to talk about resistors, talk about the thermal energy, i.e. the power which is lost due to these head-on collisions. This is all the things that we're building on top of in this lecture, or at least not this lecture, but at least in this chapter. So as we're talking through these, this is the picture that I want you to have in mind. So again, these things are to be accelerated due to the potential difference. A potential difference creates an electric field, causing these guys to then accelerate through here, trying to accelerate them through the atoms, making collisions, which means that they're constantly accelerating, decelerating, constantly accelerating, decelerating. So at the end of the day, these are going to move on average through this wire with a constant velocity, which is what we call the drift velocity. But every time that it hits, it imparts part of its kinetic energy onto the atoms, causing the atoms to vibrate more and more rapidly, meaning their kinetic energy is going to increase more and more and more, which means the temperature is going to go up. And then we're going to lose that energy that they're imparting onto these atoms via thermal energy, radiation. So this is the picture we'll be working on throughout this chapter. So yeah, the point of a resistor is simply to lose energy, which means I have to abide by conservation of energy. This thing supplies energy, this thing loses energy to make sure that I have no net loss and no net gain throughout the entire system via conservation of energy. Okay with us? So, having said that, let's start talking about some definitions. So the first thing we're going to talk about is current. So what is current? So current. What is current? So current is, we talked about this in lab before, but let's talk about it again. So if I have a wire or some electrical element, so this is an electrical element, we're then going to have charges moving through this electrical element. So I'm applying a potential difference across this guy. So across here I have some sort of potential difference. Put a battery, for example, plus negative side, which means in this case I'm going to have an electric field pointing in this direction. So it points away from the positive and then towards the negative. So in this case, if I have charged particles, and here, again, I'm going to pretend that my charged particles are positive, thanks to Benjamin Franklin. So these guys then are going to move in this direction. So inside of here, I have all kinds of different charged particles. Each one of these charged particles are moving all in the same direction. Something like this. So here, what we're going to do is we're going to cut out a cross-sectional area here. And then what we do is we define current then as the total number of charged particles which pass through this particular cross-sectional area in a given amount of time. So we then say, well, current then equal to the change in charge, which is the total number of particles which pass through in a given amount of time. So this is what we define current to be. As we talked about in lab, this thing has units of coulombs per second, which gets a special name. What's called an ampere. Now, one thing I should point out here is this is technically going to be the average current, because what can happen is that, just like when you're driving down the road, your speedometer, even though it tells you you're doing, well, let's say go back a little bit. So let's say again, if I go from here to Louisville and it takes me 2 hours to get there, my average speed then was 60 miles per hour. But as I'm going from here to Louisville, I'm going to be speeding up, slowing down, hitting traffic signs, having trailers pull in front of me, little old ladies, et cetera, which means that if I look at my velocity from moment to moment to moment, it's going to be different than the average velocity at which I would travel. So again, at one point I may be doing 80 miles per hour. One moment I might be doing 30. But again, my average would be 60 over the entire duration. So this is only true over a macroscopic time duration. But if I look at the current from moment to moment to moment, it might not be this average, it might actually be fluctuating from time to time. So the actual technical definition of current then is that it's the rate of change of charge throughout this wire. So this is the instantaneous current. This guy is what's known as the average current. Now, current is kind of a weird thing because we assign a direction to current. So for example, I would say, since my charges are moving in this direction, my current then would also be moving in that same direction. So I would say, okay, it makes sense that my current is moving this way. But current is a little weird in the fact that charge is a scalar quantity. Time is a scalar quantity, which means current itself is actually a scalar quantity. It has nothing to do with direction. So even though I say current is moving in this direction, it is not a vectorial quantity where it means it doesn't actually have a direction, but it does have a direction. So it's a little bit weird. So it turns out that this guy is actually a scalar quantity, which means no direction. Even though we do assign an actual direction to it. So what does that mean? So that means that if I had, say, 3 wires attached to each other, so here's my first wire. And then from here, I'm going to branch off to have 2 additional wires. And then I say, coming inside of here, I have a current I1 moving in this direction. Coming out through here, I have a current I2 in this direction. Coming out from here, I have a current I3 in this direction. The fact that current is actually a scalar quantity means that I don't have to care about the directions that these wires are going. Which means that I'm not treating them as vectors, saying, well, I have to look at I2 cosine of 45 degrees or whatever. All I care about is the magnitudes of these things. Now, what is true, though, is that since this is charge here, this is charge here, this is charge here, we have to actually abide by charge conservation. So a charge conservation says that the total amount of charge moving through here has to equal then the sum of the charge moving through here plus the sum of the charge moving through here. That's what charge conservation tells us. So in this case, we would then say, well, my current I1 then must be simply equal to the current I2 plus the current I3 by charge conservation. So current does have to satisfy charge conservation, meaning that the amount of currents moving through this wire has to equal the sum of the currents moving through these 2 wires. But again, since it's not a vectorial quantity, that means I don't have to care about the directions that these wires are moving, which means I don't have an I component and a J component and a Z component and etc. I don't have to worry about components. I do have to satisfy the charge conservation. So a charge conservation then says that any point like this, or as we talked about this before, this is what's called the junction. What this says then is that the sum of the charges moving into the junction has to then equal the sum of the charges moving out of the junction, which means that the sum of the currents moving in must be equal to the sum of the currents moving out. This is true at any junction. So we're going to call it the junction rule. And we'll revisit this in the next chapter. So this is current. Okay, current, again, it's simply counting the number of charges which actually move through some sort of location. So in this case, if I'm looking at cross-sectional area here, I would have current I1, cross-sectional area here, current I2, cross-sectional area current here 3. I get the total number of charges which are passing through. But since this is defined in terms of the number of charges, again, charge conservation says that this current then must be equal to the sum of these 2 currents. So again, current is a little bit weird, or it actually is a scalar quantity, which means there is no actual directional property to it. But we do treat it with a directional property. Kind of okay with us? Good. So now, let's go back to this picture here. So now we know current. Current is simply the total number of charges which passes through this in a given amount of time. So what I want to know then is, what about this thing here? So we call this thing a resistor. So how does this thing work? So what this thing says is that if I measure the current moving through this electrical element, my resistor, versus the amount of potential I add to this. So for example, if I decrease the potential, I decrease the current. If I increase the potential, I go up the maximum, then I increase the current as well. So Ohm's law then says, well, if I plotted the potential I measure versus the current, we find in this case is that these two are directly linearly related to each other. So if I increase the potential, I increase the current linearly. So this thing then says that the potential is then equal to the current times then the slope of this line, where the slope of this line is what we call the resistance. So this is the resistance of the resistor. Now, things to point out about this guy. This thing is only true in conductors. That's what we call Ohm's law. So Ohm's law is technically only true with inside a conductor. If I have some kind of material that is not a conductor, this does not work anymore. For example, if I was dealing with something like a diode, this thing actually is proportional to the current squared, not directly to the current. So if I was looking at a diode, for example, diode, in this case, if I plotted the potential versus the current, we actually then get something that looks like this. So in this case, the potential is actually directly proportional to the current squared. So again, just pay attention to the fact that here, again, this is only technically true for a conductor. What's up there?
Will we have to like work through like solving for this?
What do you mean?
Well, like, will we ever have a question? It's like you're given a non-conductive thing.
For this class, no. That's why I can say that. So no. But this is something you will see in an engineering class, for example, circuits and things. We start playing with diodes, etc. So, but again, so as far as this class is concerned, this will always be true. So even though this is called Ohm's law, it's more like Ohm's is a good idea for conductors, not really an Ohm law because it doesn't work for everything, but that's fine. So good. So for this says then that resistance then is defined as the potential per current, which is then equal to, or this is a volt then per amp, but a volt per amp has a own special name, which is what we call an ohm. So capital omega here is what we call an ohm. So those are the units then of resistance. Now, how do we measure then resistance? Well, one way you can measure resistance, again, is we take a resistor, we simply hook this thing up then to a potential source, and then we measure the current, and then we find the slope. That's then going to give us then a resistance. But it turns out there's other ways we can actually measure the resistance as well. So let's talk about what's known as resistivity. So we talked about resistivity in lab, but let's talk about it again. So our mental picture that we're going to be working with is that here is my resistor. So this is my resistor. But again, going back to this picture, inside of my resistor, I actually have atoms which are on the inside, and then I'm going to try to accelerate these charged particles through these atoms. So in this case, inside of here, I'm going to have atoms. So here are my atoms. And I'm going to connect this to a battery. So I'm going to put my battery in the opposite direction this time. There's my battery. Which means here, again, I'm going to establish an electric field. That electric field will be in this direction. So now what I'm trying to do is take this charged particle Q here, put that into this external electric field, and then try to accelerate this guy through this region here. So we know this guy's going to feel a force. This thing's going to feel the force in this direction. It's going to be our electric force because it's a positively charged particle. So we know the electric force is going to be in exactly the same direction as my electric field, which means this thing is going to feel an acceleration in this direction. Good. So as I'm trying to accelerate this thing, again, he's going to try to move, but as he tries to move through my circuit, again, what's going to happen is he's going to start making these head-on elastic collisions, causing this thing to kind of bounce around, slowly then propagate its way through the wire, kind of like in Planko. Right? Everybody ever watch? Price is Right. That's the show. They take the little disc and you drop it down, it bounces all in different directions. It's called Planko. Basically the same idea. So what happens then is this thing will eventually get through the other side, but not because it was accelerating the whole time, but because it was actually accelerating, decelerating, changing directions, and etc. Meaning that this thing on average is going to move through this thing with a constant velocity, which is what we call the drift velocity. So this mental picture gives us a way to actually then define what we call resistance. So the way I think of resistance is I think of resistance as then being equal to the probability of death. This is what I call resistance. Equal to the probability of death. So what do I mean by that? What I mean by that is, you guys ever watched the first Saw movie? In the first Saw movie, there's a fantastic scene where, turn on my lights a little bit, called the razor trap. Great. So in this case, I'm going to show you a little bit of the razor trap. So basically what happened here is there was this poor sap that got taken by Jigsaw, right? He was put in there and he was told that he has to try to crawl all the way through this trap, which has crossed razor wires, where he has to go from one side to the other side without dying. Okay? And if he can make it in a certain amount of time before the thing actually closes, then he can relive his life again. Obviously, he's dead here, so he didn't actually do that. But this is a great kind of imagery for what it is that we're talking about here, which actually talks about this probability. This is actually resistor. So resistor then is the probability at which this electron or this charged particle is going to make it from one side to the other side. So this is what we want to talk about when we think about, is this thing going to make it through or is it not? Probably enough imagery on that one. Great. Okay. So this is my probability of death that we're going to talk about. So let's think about that when we talk about resistance. So resistance then is we're going to think about this guy. Here's my guy. Here is my razor wire trap. So here's my razor wires. And let's think about what's the probability that this guy is going to die? So meaning he's not going to make it through this death trap. And let's think about the parameters that go into our death trap. So the first thing that's going to go into our death trap is the length of this death trap. So let's think about this thing. So this is going to have a length to it, L. This thing is also going to have a cross-sectional area of A. And finally, this thing is going to have a density of the wires that we're going to call rho. Right? So rho in this case is equal to the density of wires. So let's think about the probability of death. So first of all, how does his probability of death depend on L? So meaning, if I increase the length of this, is his probability of death going to increase or decrease? It's going to increase, right? So the first thing I can say then is, well, this thing is then directly proportional to the length, right? So the longer I make this thing, the more he's going to likely die. Great. What else? Let's think about the cross-sectional area. So if I fix the density, if I make the cross-sectional area bigger, what happens to his likelihood of death? Is it going to go up or go down? It's going to go down, right? The bigger I make the cross-sectional area, the more wiggle room he can find his way through, which means he has a more likely chance of actually going through. So does that mean it's directly proportional to the area or inversely proportional? Inversely, good. So I know this thing is also then inversely proportional to the area. What about the density? So if I increase the density of the wires, meaning if I start putting in more and more wires here, what happens to his probability of death? Is it going to go up or go down? It's going to go up. Fantastic. So I know this thing is also then directly proportional to the density. So if I put all these things together, this then tells me that resistance is then equal to the density times the length divided by the cross-sectional area. So again, L here is equal to the length of the resistor. A is the cross-sectional area of the resistor. And then rho here is not what we call density, but this is what we call resistivity. It's kind of like a density. So if I do some dimensional analysis, what I know is I have to have omega on this side. On this side, I have a meter divided by meter squared, which means this is equal to rho divided by units of a meter, which means that rho itself then has to have units of ohm meters. So this is what rho is. So I need that extra meter here to kill out the meters from down here. So in a way, resistivity is kind of like a density, but what resistivity actually tells me is how good of a resistor of my object. So if I have a resistor, the higher that the resistivity is, the bigger or the better the amount of resistance that this thing has. It's a better resistor. So here, this says then that rho is a measure of how good of a resistor my element is, my resistor is. So in this case, again, if we have a high resistance or resistivity, this gives me a high resistance, which means it's a good resistor. If this thing has a small resistivity, that means it has a small resistance, which means it's a bad resistor. Now, from here, we can define something which is known as the conductivity, which is called sigma, where sigma is equal to 1 over the resistivity. So what's conductivity then? So conductivity then is a measure of how good of a conductor an object is. So it's how good of a conductor it is. So what does this thing say? This says that if I have a high resistivity, which means it's a very good resistor, this thing is a really crappy conductor. Because if this number is big, then it's 1 over a big number, which makes this thing really small. But if this thing is a very poor resistor, which means it has a very poor resistance to it, that means it's a very good conductor. So one thing you'll find is that metals, for example, will always have a very small resistivity because they're very good conductors, as opposed to something which has a very small very large resistivity, something like a plastic has a very large resistivity, because it's not a very good conductor, but it is a very good insulator. So these two things are vice versa from each other. If one thing is a good something, it's a bad something else. Now, it also turns out that resistivity is temperature dependent. So this guy is actually temperature dependent. Resistivity is temperature dependent. Which means that the resistivity at a given temperature is equal to the resistivity at some reference temperature times then 1 plus alpha times then the change in temperature, where alpha here is the coefficient of thermal resistivity. So T0 here, so in this case, delta T is simply equal to the final temperature minus the initial temperature. So this is its initial resistivity at the initial temperature, and then this is its final resistivity at the final temperature. Alpha here is simply a constant, as well as rho is most of the time. So every different material will have its own different rho value, which means every different material will have its own different resistivity to it. But every different material also has its own different coefficients, which means that the rate at which it changes under thermal changes will be different depending on the type of material that it is. Now, one thing I should point out here is that even though we're treating alpha here as a constant, it's actually technically not a constant because this thing is only constant over a range of temperatures. Which means as I start going to different temperatures, this constant will actually change over different changes of, or different ranges of temperatures. But as far as we're going to pretend in this class is that it's actually constant, because we're only going to use it over particular amounts of pardon me, temperature ranges. So basically, this is just a number you would look up. This is also just a number you would look up, or it would be given to you in a particular problem. Okay with this? So basically what this thing says is as the temperature gets higher, the resistivity gets higher, which means the resistance also gets higher. So because this guy is temperature dependent, that means the resistance is also temperature dependent. Means that our resistance at a given temperature is then equal to the resistance at the initial temperature times 1 plus alpha times the change in temperature. So this is how the resistance changes with temperature. So okay, this is just the resistance at the initial temperature. This is the change in temperature, final temperature minus the initial temperature. This depends on the type of resistor I have. So if this was a nichrome wire or something else, gold wire, etc. And then this is the resistance at the final. So again, as the temperature goes up, the resistance goes up. By Ohm's law, then, if the resistance goes up, the current then goes down. So those guys are inversely proportional to each other. So great. Let's use all this. And let's do our first example. So this says that we want to connect our stereo to some speakers on the other side of the room. So in this case, we're going to use a wire. That wire is 20 meters long. And we want to know what is the diameter of the wire that we should use if we want our resistance to be less than 0.1 ohms. And then finally, we want to know if the current in each speaker is 4 amps, what is the potential difference or potential drop, I should say, across the wire as it goes from the radio to the speakers. So good. So let's draw our situation. So here's our stereo. Here's one of my speakers over here. So what I know is that this length from here to here is a length L, which is then 20 meters. And let's see, what else? I tell you what type of wire this was? Copper wire. So we know this thing is made out of copper. So here we're going to have a resistivity of that of copper. That is a second. And what we want to know in this case then is we want our resistance to be technically less than 0.1 ohms. But we're going to set it to 0.1 ohms. So we want our resistance then to be equal to 0.1 ohms. So what I want to know in this case then is, if I was looking at the wire, so let me blow up a section of the wire here, I want to know what is the diameter of this wire. So what's my diameter across here? So what's my diameter D? So numbers we need to know are resistivity of copper is equal to 1.68 times 10 to the minus 8 ohm meters. So this is my resistivity of copper. So good. So what do we know? So we now know that the resistance is equal to the resistivity times the length divided by the cross-sectional area.
Can you get the resistivity there?
Oh, I just looked it up. Oh, you wanted to put it back so you can see what it was? Yeah. Go. Okay. Sorry. So show that guy. So good. So we know that resistance is equal to resistivity times the length divided by the cross-sectional area. So we know the length. We know the resistivity, we know the resistance, so the only thing we're looking for in this case then is the area. Or particularly, we want to know what is the diameter. So, how many of you have ever seen a wire before? Okay, what is the shape of a wire? It's a cylinder. So what's the cross-sectional area of a cylinder? Pi r squared. So great, let's put all that together. So this guy's going to be equal then to resistivity times the length divided by pi r squared. But what I want is the diameter, not the radius. So how does the radius compare to the diameter?
I squared.
Good. So what I know is that the radius is half the diameter, which means the radius squared is equal to the diameter squared divided by 4. So that 4 is going to move to the top. So it's going to be 4 times the resistivity times the length divided by pi times the diameter squared. Good. From here, the only thing I need to know then is what is the diameter. So let's solve this for the diameter. So it says my diameter then is going to be equal to 4 times rho times L divided by pi times the resistance all squared. So this is going to be my diameter. Plug in my numbers. What I get in this case is this works out to be about 2.02 millimeters. So this is my diameter. So this represents then the greatest, actually, so if I make it smaller, then make that bigger. Right, so this represents then the smallest radius that I can use, or the smallest diameter. Because again, what I want is the resistance to be less than 0.1, which means the bigger I make the diameter, then the less the resistance is going to be. So this is then the smallest diameter that I can actually use. So good, so this is part A. So now what part B is then saying is, what I find then is I have what? A current running through here. So my current then, saying in this direction, is equal to 4 amps. What I want to know then is, if I measure the potential difference between the stereo and the speakers, what's the potential drop? So how much does the potential drop going across this wire, going from my stereo then to my speakers? So what would I use in this case? Ohm's law, right? So in this case, for part B, I would simply say, well, Ohm's law says that the potential drop is equal to the current times the resistance. In this case, I know the resistance. I also know the currents, because my resistance is 0.1 ohms. So that means I can easily find my potential. So it's going to be 0.4 amps times 0.1 ohms, which is then going to be 0.4. Nice. That was okay?
What was the question?
So the question was, let's come back up. So this says that if each wire was carrying a 4 amps of current, then what is the potential difference or the voltage drop across each one of the wires? So I'm just applying Ohm's law in this case. Okay.
So that means that over the whole length of 20 meters, it loses 0.4 volts.
Correct. That's right. Exactly. Okay.
Why does it say each wire?
Well, because there's technically 2 wires, but each one is supplying the same amount of potential. So one wire is going to lose 0.4, the other one's going to lose 0.4. So they would both lose the same amount. So here we're only concentrating on both, because they both do the same thing. Okay. Now let's go back to currents. Now, one interesting thing about currents is that when I defined currents initially, so let's go back to this picture. What we said was that all we're doing here is we're cutting out a cross-sectional area, and we're counting the total number of charges which pass through this cross-sectional area. But the cross-sectional area is the entire length of the wire. This is how we define current. But as I have kind of drawn here through all my squiggly lines, notice that at different positions across the wire, at least across this cross-sectional area of the wire, I could have different amounts of charged particles flowing through that portion of the wire. Meaning I could have no particles moving through the top, maximum amount of particles moving through the middle, or I could have maximum at the top, no moving through the middle, or etc. So the current tells me only how the charged particles are moving across the entirety of the cross-sectional area of the wire. It does not tell me, though, how the charged particles are actually moving throughout any portion of the wire itself. Which means, if we want to know that, we have to come up with a new quantity. And that new quantity is what's known as the current density. So let's talk about current density. So the current density tells me then is how the charged particles are moving through my wire from position to position. So this is how the charged particles are moving through the wire, through the electrical elements. From position to position. So again, current actually tells me what it is on average over the entire cross-sectional area, but the current density tells me what it's doing from position to position. Which means that, again, if I was looking at my wire, so let's say here is one wire or electrical element, and here's another wire or electrical element that is here, it may turn out that, again, in this case, I have maximum amount of charges moving through the center. And as I move toward the outside, I get smaller and smaller and smaller until eventually I have no charges moving on the exterior. And on this side, it would just be the mirror image on this side. Or it may turn out that actually I have maximum on the outside. And then again, as I start getting closer and closer to the center, this thing is actually going to drop, and then maybe I have a little bit moving through the center. But then it increases again as I move toward the outside. So this is different possible profiles of how the charges are actually moving from a position to position point of view. But again, the current itself is the average over this entire cross-sectional area. So from this, we're going to define then what's called as the current density. So the current density then, J, is then going to be equal to the current per unit area. This is J. So this has units then of amps per meter squared. So this is my current density, current per unit area. Now it turns out though that unlike current, which is a scalar quantity, J actually is a vectorial quantity because it does point in an actual direction. So if I want to then find the current from this, the current then is equal to the integral of the current density dotted then by the differential area. This is the relationship then between the current and the current density. So what is my differential area in this case? So what I'm doing in this case then is, as I go back to this picture, in this case then I would be taking a differential area. So here is my cross-sectional area. I'm going to chop this thing up then into a small disk, like we have done many times before. So this is going to have a thickness then of dr, and this is going to be at a radius of little r. So in this case, my differential area then is then going to be equal to what the circumference of that circle times the thickness of that circle. So that's the same thing then as 2 pi r times dr. So this is my dA. My dA is going to be, again, this little ring here that I'm going to stack on top of each other and simply add them all the way through. What's up there?
Will this be true for any time we use this?
Yes. This is the only geometry we're going to look at it for. Now, there are much more complicated geometries, but we're not going to go there. So as far as this class is concerned, this is all we're going to use. Okay? What's up?
Does that R just go to the inner circle?
Yes. Yeah. So R is talking about the size of this disk, and I'm drawing here. Yes. Exactly. So the size of that ring, I'm actually drawing, I should say, not disk. Good. So again, all we're doing then is we're calculating the current through each one of these individual rings and then simply summing them all together to get the total amount, which is in there. Now, notice for our circumstances though, dA is also going to point in exactly the same direction as the current itself, which means if I drew a dA vector on this guy, dA is going to point in the same direction as my current density. So this is my current density, which means my dot product between the two of them is simply going to give me 1. So again, for our purposes, this is going to be the same thing then as simply the integral of the magnitude of the current density times 2 pi r dr. So this is going to be our relationship between the two. Again, as far as this class is concerned. In a general setting, not so much. Okay? What's up there?
Is J ever going to realign R?
Yes.
So you're going to, so the 2 pi can be taken over.
Correct. But the R and everything else will have to stay. Exactly. So this is going to be the same thing as 2 pi integral J R D R, well, J will in general be a function of R. Correct. As again, we can see from these pictures here. So in this case, J is a function of R, it's changing as R gets bigger. Same thing as in here. So let's use this, let's do a couple of examples. Let's see how this actually works here. So let's look at our first example. So this says that we have a wire which has a radius of capital R, which is equal to 3.4 millimeters. And then we're told two different magnitudes of current density. So the first one says for part A, we have JA is equal to some J0, where J0 is just a number. That's 5.5 times 10 to the fourth amps per meter squared. Times then the radius we are away from the center axis of that wire. So that's little r divided by the radius. Or in part B, this is again the same J0, but it's going to be 1 minus r divided by capital R. So A here corresponds to this picture. So this is actually we're looking at for part A. Right? So in this case, actually no, scratch that. This is part A. Because here it's at 0 at the center, but then increases linearly as we get bigger. Okay. Part B is actually this picture. So when R is equal to 0, I have maximum. And then as I go to the outside and get to capital R, this thing goes to 0. Okay, so this is actually our picture for part B. This is our picture for part A. So good. So in each one of these cases, all I want to know then is what's the current? So I want to know what is the current when I have this profile and what's the current when I have this profile. So let's look at each one of those. So let's look at part A first. Part A, we have J is equal to J0 R divided by R. Now, what we know is that we want to know the current. So we're looking for the current, which we already wrote down as 2 pi times the integral of J times R dr. Now, in this case, we're going to integrate from the center, which is at 0, to the radius of this object, which is capital R. R, we now know is J0 divided by capital R, which are both constants, so we pull them outside, which is then going to give me simply an R. So it's going to be equal then to 2 pi J0 divided by capital R, integral from 0 to capital R of R times R, but what's R times R squared, good. dr. What's the integral of R squared dr? Good, R to the third over 3, so it's going to be the same thing then as 2 pi J0 divided by 3 times R times capital R cubed. Here, this R is going to cancel this one, so I finally get then that my current is going to be 2 pi J0 divided by 3 all times R squared. From here, I simply put in my numbers, calculate. What I find then is that the amount of current is equal to 1.33 amps. So this is my current running through this particular wire.
Did you get the value for J0?
Oh, J0 was given at the very end. So that was the 5.5 times 10 to the 4th. What's up, person?
How did you get the, on the second step, the 2 pi J naught over all side? How did you get the J naught on the side?
Oh, because, so yeah, if I go back to this structure here, J0 and R are simply constants.
Oh, you just told me.
Exactly. So I'm just plugging those guys directly in here. That's what gave me the R squared because I already had an R here times that R, which gives me the R squared. Okay. Look at part B. Part B then says we're going to do exactly the same thing. So again, we know our current is simply going to be equal to the integral. Let me write J down first, actually. So J in this case is J0, 1 minus R divided by capital R. The current then is going to be equal to 2 pi times J0, because again, J0 is a constant, I can pull it outside. Integral from 0 to capital R of then 1 minus R over capital R, R dr. Okay, so I'm just inserting what J is. J0 is a constant, so I'm pulling it out, writing it this way. Again, here it's probably easiest to do this as two separate integrals. So I'm going to have the integral of simply the first one, which is going to give me an RdR, and then I'm going to have the integral of the second one, which is an R squared. So this is going to be the same thing as 2 pi J0 integral from 0 to R of an RdR minus 1 over R integral from 0 to R of R squared. Okay. What's the integral of RdR? Good. R squared over 2. Good. So I'm going to get a 2 pi J0. This is going to give me an R squared over 2 minus 1 over R. And then I have the integral of R squared dr. But what's the integral of R squared dr? You already told me there was R cubed over 3. Good. So this R here is going to cancel this R. It's going to make that an R squared. So I'm going to factor out the R squared. So finally, I'm going to get the current then is going to be equal to 2 pi J0. Factor out the R squared. And I'm going to get a 1/2 minus a 1/3. Here's subtract those. Best thing to do is find a common denominator, which is 1/6. So I'm going to get a 3/6 minus 2/6. So what's a 1/6? Or sorry, 2/6 minus, I can see, a 3/6 minus a 2/6. 1/6. So it's going to be the same thing then as what's 2 pi J0 R squared over 6. Now, if I want, I can cancel the 2 with that to make it a third, but I'm not going to do that because notice that if I go back to this answer, this one was over 3, this one is over 6, which means this current is half the size of this current. So this is 1.33, and then the other one is 0.666. 0.666. It's half the size of the other one. Right? So this is current density. So again, current density tells me how my current is actually flowing through, or how the charged particles are flowing through the wire from position to position to position to position. Current is the average over all of that over the entire cross-sectional area of this particular wire. So this is the difference between all of them.
Can you compare it with the
Sure.
last please?
To the question?
No, that was,
No,
thanks.
okay. So I'll see everybody tomorrow. We'll start talking about drift velocity, how this relates to velocity at which particles flow through. And then yeah. Okay, that's fine. I have to report in the next couple of weeks anyway, so.
Okay.
So, yeah. When I gotta post it, I'll just let you know.
Okay, thank you.
You're scared to ask me.